Today we're going to learn how to solve a matching problem using a maximum flow network. So we have 5 people, K, C, B, R, T, S, M, J, and T, C, and 5 other people, L, A, M, S, K, H, L, E, and V, P. And we want to match them up. We want to make 2-person matches. Now, KC is only compatible with MS. BR is only compatible with LA. TS, however, is compatible with LA and MS. And TC is only compatible with KH, LE, and VP. So we want to make the maximal number of matches. And we have to make sure that we only match up 2 people that are compatible, that have a C here. Okay, so it's not easy to solve it in this form, but it can be transformed into a maximum flow network problem. So let's see how it works. So we have our row people right here, the 5 row people, KC, BR to TC. So that's this row here. And we have our column people, LA, MS to VP. These are the column people. Now, the source is where the flow comes from, and the sink is where the flow goes to. Now, from the source, there's 5 units coming out of the source, and the capacity, think of it as the maximum that can come out of the source is 5 units. So the capacity from source to each of our row people is 1. And KC is compatible with MS, so we have a connection from KC to MS. MJ is compatible with LA, MS, and VP. So you can see that there's 3 connections, MJ to LA, MJ to MS, and MJ to VP. So let's just double check that. I think I might have missed one. So we should have MJ to LA, MJ to MS, and we should be MJ to VP. MJ to VP, no, so let's add that. So there should be one more option here. Okay. All right, so then from each of the column people, there is a connection to the sink, and the capacity is 1. So let's see what a match would look like. So suppose we match KC with MS. Then we'll flow 1 here. 1 unit will flow from here to here, and that 1 unit will flow from here to here, and that unit will flow from here to here. Now, because only 1 unit can possibly flow into each of these row people, they can only match with 1 of the column people. So you have 1 unit flows here. That unit's going to either flow this way or this way, and that means it's choosing only 1 partner over here. And on the other hand, could MS accept 3 partners? The answer is no, because it can only have a capacity to continue on with 1. So the bottom line is we're going to match up each of these people with at most one of these people, and each of these people will get at most one of these people. And we'd like to match up as many people as possible, so we would like to flow as much units as possible from the source to the sink. So let's give it a try. So we start out by simply trying to increase the flow. So let's flow 1 from here to here, and then 1 from here to here, and then that one only connects to MS, so we'd have 1 from here to here. Okay. Next, BR. BR can only match up with LA, so let's see. The 1 will come out of here, and 1 will come out of here. Okay, TS. TS has a choice of LA or MS. They're both taken, so it looks like TS is not going to be able to match with what we've chosen so far. All right, MJ. So MJ would have to go to VP, it looks like. So MJ will go along here. Okay. And TC, looks like TC can go to KH or LE. So let's go to LE. Let's go to VP. All right. Oh, I already got VP, sorry. VP is already taken. So let's match up with LE. Alright, so we've made 4 matches, right? So we've made 4 matches. So this one over here, in parentheses, is the flow through this arc. And, you know, for example, MJ matches up with VP. TC is matching up with LE. Okay, so we have a flow of 4. Is that the maximal flow? Well, we need to find the minimal cut. So how do we find the minimal cut? Okay, so we start with the reachable nodes. Which nodes can be reached? By definition, we can always reach the source node. Okay. From the source, we cannot go directly to KC or BR because those pipes are full, those connections are full, those arcs are at full capacity. The only one we can get to directly is TS. So TS is by definition reachable. We can reach it. Okay, from TS, where can we reach? Well, these pipes, think of them as pipelines, and we're flowing oil through them. These pipelines are free. We can flow through here or here. So TS goes to LA and MS. So that means MS is reachable and LA is reachable. Okay. Now, where can we go from LA? Well, remember, we can backflow, right? So from LA, we can look at going back here to BR, and this is where we came from. So it's a little bit counterintuitive, but because there's an arrow, there's an arc that goes from BR to LA, and this arc has a flow on it, you can reverse it to reach BR. So that means it's possible to reach BR by using the backflow technique. So BR is reachable. Okay. Going back to TS, we can get to MS. MS, you can backflow from MS back to KC because there's a positive flow on this arc from KC to MS. So what that means is KC is reachable. Alright, so let's just double check that we got everything from LA. We went back to BR. From MS, we went back to KC. And let's just double check that there's no way to reach KH, LE, and VP. So TC, the only way to get to KH is from TC, and TC is not reachable. The only way to get to LE is from TC, and that's not reachable. VP, the only way to get to VP is from TC or MJ, but MJ is not reachable either. Okay, so the blue nodes are the reachable nodes. It's possible to flow there without violating the capacity constraints. So once we have that taken care of, we can now shade in the other nodes red. And these are the unreachable nodes. So the red nodes are unreachable. It's impossible to flow to them. Okay, so the cut, in order to find the minimal cut, what we have to write down is the arcs that go from a blue node to a red node. So I'm going to erase this. We don't need this anymore. So let's look at the arcs from a blue node to a red node. So let V prime equal the set. So let's see, blue to red. So source to MJ. Source to TC. So remember, we're going blue to red. So these blues go to other blues. Go to other blues. So LA to S to sync. And MS to sync. Okay, the capacity of this cut, so this is the minimal cut. This is the minimal cut. And the capacity of this cut is 1 plus 1 plus 1 plus 1, which is 4. So the capacity of the minimal cut is equal to the flow. So that implies that this 4 is the maximum flow. So that's it. The best you could possibly do is 4 matches. You cannot do any better than that. Alright, so our next problem is a lot easier than this one. It's called the minimal spanning tree. So first of all, what is a tree? Well, let me show you what's not a tree. Let's make this an undirected graph, so we won't have arrows in this case. So this is not a tree. This is not a tree. It is a graph. So what makes it not a tree is that it contains a loop. Now if we erase one of these arcs, it's now a tree. So this is a tree. A tree is a network or a graph without any loops. Now what is a loop? A loop means that there are 2 ways to go from one node to another node. When you don't have any loops, there's only one way to get from node 1 to node 3. So this is called a tree. So let's look at another example. So A, B, C, D, E. And let's connect them with a lot of possible connections. And you could have more like this. And let's give them some numbers. So the distance from A to B is 4. 3, 2, 4, 6, 2, 2, 8, 6, and 1. Alright, so what we're trying to solve here is what's called the minimal spanning tree. Imagine that these are 5 cities, and each of these arcs in our graph, in our network, is a possible road you can build to connect the 5 cities together. Now, we obviously don't need this many roads. We just need to make sure the cities are connected. It's perfectly fine that in order to go from A to E, you can first go to B, and then maybe to D, and then C, then E. It costs a lot of money to run the roads, and we want to connect them with the minimal amount of pavement, of road. So which of these roads should we really build, and which ones will never be built? So think about which ones should we erase so that the 5 nodes are connected by roads, but not necessarily by direct roads from city to city. Okay, so this is the minimal spanning tree algorithm. It's actually one of the easier algorithms. Start with any node. Let's say node D, and shade it in. Okay, from node D, what is the nearest neighbor from a shaded to an unshaded? Well, from D, you can go to A, B, C, or E. The closest neighbor to a shaded to any unshaded is 2 miles from D to E. So the conclusion is we add we add node E to the shaded set, and the way that we add it is from here to here using the distance 2 road. So we use the road that's only 2 miles. Okay, now from any shaded, not just E, but from any shaded to any unshaded, what is the nearest neighbor? Well, 4, 3, 6. From E, it's 2 and 8. Out of all those numbers, 2 is the lowest number. So we would next go to C. Okay, now from C, we can go, remember we always go from a shaded to unshaded. Never shaded to shaded, that would generate a loop. That will ruin your tree. Okay, so what do we have from D? It's 4, 3. From E, it's 8. From C, there's a 1 right here. So that's the smallest. So let's use this one, and we'll shade in B. Okay, so we're left with going from shaded to unshaded. So we can go from here to here, which would be 4. From C to A would be 2. From B to A would be 4. 2 is clearly the smallest, so we would use this connection. Okay, so everything is shaded in. All nodes are connected. And let's write down the length of our minimal spanning tree. So it will be 2 plus 2 plus 1 plus 2. And I think I got everything right. I checked off each number as I wrote it down. So 2 plus 2 plus 2, 6, 7. So 7 is the length of the minimal spanning tree. So the answer to this question is 7. It's the length of the minimal spanning tree, MST. All right, let's try another example with a few more nodes. And some ties. Alright, it's a little bit more complicated. Let's give it a try. Alright, so let's start anywhere. Doesn't matter where. So let's start at A this time. Alright, so we're starting at A. And we shade in A. Okay. From A, the closest neighbor would be 3, 6, or 4. 3 is the answer. So reinforce that connection and say 3. In fact, we could just say 3 right here. Okay. From G, there's 4, but there's also a 4 here. Remember, it's not just what's the closest to G. It's what's the closest neighbor to the shaded set. So A is 6 and 4, G is 4. You could choose C next, or you could choose F next. Just choose one. Break the tie, but do not choose both. So let's go to F. Let's reinforce this, and we'll have 4. Okay. From G, 4. From A, 6. From F, 2 and 2. 2 is the winner. Choose one of these. So let's go to D. Alright, so plus 2. Okay. From D, there's 2. D, there's 3. F, there's 2. So we have a choice. 2 is the smallest from any shaded to any unshaded. So let's choose this one next. So reinforce that, plus 2. Okay, from shaded to unshaded there's 3, 8, 4, 6, 2. 2 is the winner, 2 is the smallest. So use this one, shade in E, and add another 2. Okay, from shaded to unshaded there's 3, 8, 6, 4. 3 is the winner, that's H. So add 3 next. Alright, 12, no. 2. 2 is the smallest possible neighbor, so we will go here next. So plus 2. Alright, there's only one unshaded node left. Either 10 or 12. Well, 10 is the lower, so shade it in, and plus 10. So this is the minimal spanning tree, 7, 9, 11, 13, 16, 18, 28. So 28 is equal to the length of the minimal spanning tree. All right, so this concludes minimal spanning tree and solving matching problems with maximum flow.